All right, let's get started. Good morning, everybody. Welcome to Chem 1211 with your host, me, Dr. White. All right, a couple important things. First of all, I already sent out the email with the password for test number one. You'll have until I think I put in there 10 o'clock tomorrow to hand it in, or 11. I forgot which I have my email. If you're a couple minutes late, that's okay. Just don't hand it in on Sunday. I'll take off points. As per my announcement recently, I want it uploaded as a single PDF file. I have files on Blackboard, which I've sent out to you in the announcement directing you how to do that. If you're not sure, email me. I'll be checking my email the rest of the day, about every 2 hours till 9 o'clock tonight, if you need help or if you have questions. But if you don't upload it as a single PDF file, I reserve the right to take off up to 25 points. It's a lot of extra work if you don't, and trust me, I don't need it, and that's why. And I did that during the summer. So students were able to do it by my instructions. All right, another thing, as I try always to do, which I do usually, if you look later today, I've already uploaded your lab number 2 scores. Remember, maximum was 11. As I always tell you, there's no such thing as a dumb question. If you have any questions about any of your grades, always feel free to ask me. I see one question right now. Yes, the question from one of your colleagues was, when you say a single PDF, yeah, you're going to have, what is it, 9 pages, I think, 10, I forgot which right now off the top of my head. Oh, it's not up there. Awful humor Thursday. But anyways, what I don't want is 8 or 9 different picture files. Just the PDF will have all the pages of the test, so it will be better be more than 1 page, or you're not going to get a good score. And if you do not have a printer, don't write out the questions of the test. Just put on a paper problem 1, like a 1, and then put your answer, then 2, 3, and so on. So if you don't have a printer, if like me, my printer died and I haven't had a chance to replace it, you still can do the test. All right, any other questions about test number 1? Well, Andrew, you should, if you do it correctly, have 1 PDF file. If you have a scanner, at least the scanners I've always used, combine them in one. If you have a cell phone, I've given instructions how to combine everything into 1 PDF. So what I don't want is 9 PDF files, 1 for each page, or 9 pictures. Does that help? Oh, I misinterpreted what you said. Thank you for sharing a link. Andrew, if you look at the chat, has done it, and other people are now jumping in. Thank you. Thank you all for your help. One of the things I think I mentioned, I just finished up last night and this morning, this awful course I had to take, awful because spent way too much time for what they taught me, but the other school required for online teaching. And it's been taking a lot of my time. That's done. I'm going to have more time, and I'm going to come up with some things I'm going to do with you people to help me learn about you and you learn about me. I think that part you already know a lot about, but I want to improve in socialization in our class, and I think I'll be able to pull it off. One of the common questions I got, and I put out an email, I think, or I'll say it again. Yes, anything you have to calculate, use a calculator. That's why I taught you how. Also today, if you have any last minute questions, I'll stay a few minutes after class. All right, anything more on test 1? And don't forget, And the lab that we went over last Thursday is due today. Make sure you get it in today or maybe even tomorrow if things are getting tough for you. I didn't say that, did I? Yes, I did. All right, let's get started. Now, I was talking about ions. Ions are formed, again, this is material that'll be on test 2, which is coming up in a couple of weeks. Seems like every couple of weeks there's a test, so I have 4 tests. But anyways, I was talking about positive and negative ions, and negative ions is where an element gains 1 or more electrons, and when it does gain, it becomes negative, and we call that an anion. And I showed you similar to cations how it goes. And let's do one. First of all, I thought I had it open, but I don't, so hang in there. All right, let me just get this a little larger. And hopefully, can you all see the whiteboard, what I just wrote? Give me a thumbs up if you can see it. Thank you to my thumbs up people. And the question is, what ion does bromine form? And let me help you out a little. You have to look at the periodic table. And by the way, you should download and use this PDF periodic table for test number 1. You'll also get it for 2, 3, 4 in the final. So the first thing you have to do is, where's bromine? Oh, it's Br. It's right there. Then you have to figure out how many electrons and protons does bromine have. Look at the atomic number. Now, what's the nearest noble gas? I'll let you figure out how to find that, and then I'll tell you. Time's up. And that is, what's the noble gas, this column, that's closest numerically to the atomic number of bromine? You have krypton 1 away, argon a lot more than 1, and xenon a lot more than 1. So the answer is krypton, which has 36 electrons. So now what do? Remember, atomic number tells you how many electrons, how many protons. And probably I'd write up here, instead of what ion, I'd write the ion. But anyways, and you learned that krypton has 36 electrons. And I'll let you do the rest to figure out what ion does bromine form. And when you're done, give me a thumbs up or smile if you have your video on, or you can do both. And before I forget, for those of you who celebrated this Friday night at sundown is New Year's, so the standard greeting is Lashana Tov, which means Happy New Year's. So if you do celebrate it, I hope you have a happy and healthy New Year's. If you're not sure what I'm talking about, look up the high holidays in Google and you'll find out. All right, let's do this. Bromine wants to have the same number of electrons as the nearest noble gas, an octet, 36, but it will not lose any protons. Each electron, -1. Each proton, +1. Do the math. -1 times 36 is -36. +1 times 35 is this. Add it up, you get -1. How do you show that? By a minus sign. And the answer would be this. And now you know how to do, oh, let's do one more. These are fun. And I'll just leave this on here. Why don't you do nitrogen? What ion does nitrogen form? And I'm going to let you try it all by yourself first. See what a nice person I am? Is that better now? Can everybody see the table better? This way you don't have to get your magnifying glass out. And when you're done, give me a thumbs up. I see some people are done. Please be patient. I try and give everybody time to finish. The rest of you, hurry up. No, I'm just kidding. All right, I'm seeing a lot of thumbs up, so let's go forward. The question is, what ion does nitrogen form? Nitrogen N. 7 electrons, 7 protons. How do I know that? The atomic number in the upper right-hand corner of this periodic table. What's the nearest noble gas numerically? Closest by atomic number. You have helium 2, neon 10, argon 18. What's closest? Neon, it's only 3 away. So, by the way, this is a symbol I picked up somewhere, meaning the end of this problem as opposed to drawing. So nitrogen, it has 7 electrons, 7 protons. It wants to go to the same number of electrons as the nearest noble gas, neon, and that's 10, but it will still have the same number of protons. Each electron is a -1 charge. Each proton is a +1 charge. Do the math. Add this up, and you get a -3. Therefore, the answer would be either this, or you could write it this way, which is the newer way. Dr. White likes the older way, but either one would be correct on my test. I don't force people to do what I like to do when it comes to when they've had a change over the last recent years in how they write things. All right, now you've learned about ions and how to calculate how to form which ions are formed from which elements. And the question you should ask is, so what? Why am I learning this stuff? Well, the obvious answer is you want to get a good grade because you want to get into program or school. But why learn about ions? Let's find out. And let's talk about ionic compound formation. Remember, there are two types of compounds, ionic compounds and covalent compounds. Actually, there's three. You can have a mixture, but we'll talk about that later on. And ionic compounds are formed when atoms donate electrons and other atoms accept those electrons. So if I'm an atom and I want to get stable and you're an atom, I could say, hey, take my electrons. And if you needed them, you say, sure, I'll take them. And you both become ions. When such an electron transfer occurs, then positive and negative ions attract one another, forming an ionic compound. So when you have two ions, positive and negative, they attract each other. How many of you have ever played with magnets? Only a few of you. You're missing out on a lot. When I was a kid, I loved them. I still love them. You can't see over there, but on the side there, I've got a bunch of magnets. And over here, when I get from friends old hard drives that don't work, I take them apart and take the magnets out. Well, if you've ever played with a magnet, two magnets, say a bar magnet, that's like a bar, and they have bars. Let's assume the tips are north and this is south. It's like on a compass. Well, if you put the two north together like this, I'll say, no, we're the same. But if you go like this, north and south, whoop, they come right together. Very expensive demo. Not really. But anyways, ions are the same way. Positive, negative, they say, whoop, let's get together. And they form an ionic bond. And ionic compounds are positive and negative ions held together by strong electrical attraction. It's called Coulombic attractions between opposite charges, and this is called an ionic bond. Remember, an ionic bond is a transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. Now, when you form an ionic compound, charge balance is important. And this dictates what the molecular formula is, like sodium chloride. Why is there only one sodium and one chlorine? Well, we're going to find out, or chloride. It indicates, the formula indicates the number and kind of ions that make up an ionic compound. Settle hint time. The sum of all ionic charges in a formula or any molecule is always zero. All molecules have a net zero charge. I have it on. I'll write it right here. All molecules have a net zero charge. That means the ions have to neutralize or balance each other out. For those who are taking notes, write this down. And this is a fact, and it's the truth too. Ooh, I forgot. I haven't used that in a long time. I work for a company, and when one person in a meeting really wanted to slam someone else, they say, no, this is a fact, and it's the truth too. Anyways, when we're looking at molecules and their subscripts, the formula of any ionic compound always has a zero overall or zero net charge. The subscripts of the formula are used to obtain overall zero charge. So in continuing that concept, the subscripts of a formula are used to obtain zero charge. I'll go back here in case you were writing this down. Remember, anything you see on the screen here in terms of what's printed is available in Blackboard. These right now are from the lecture folder for the files in that folder. All right, so what does this really mean? Let's move over to the whiteboard. Did you notice that was named after me? Oh, that was awful. Oh, that was awful. That. All right. All right, I'll do this one, another one, then I'll let you have some fun. You know, I do share. Now, the question is 3 points each. Write the formula for the molecule formed by, or I might say formed by the following ions. And notice we have sodium plus and chloride minus. And earlier we went through and I showed you how to find out what ion does sodium form, what ion does chlorine form. And it always forms this, nothing else. If you find any others, let me know, we'll be very rich. No, they don't. So what do you know? All molecules have a net zero charge. It's important enough, I'll say it twice. All molecules have a net zero charge. Therefore, the sodium has a +1 and the chlorine has a -1. Does that add up to 0? And the answer is yes. So that means in a molecule with sodium ions and chloride ions, the formula would be this. Oh, look, it's table salt. And as you've heard Dr. White say, if you're out to dinner, lunch, or breakfast with me at a restaurant, which hopefully sometime next year we'll all be able to do, and I'll ask, could you please pass the NaCl? And this is why sodium chloride is NaCl, because the sodium cation and the sodium anion, one of each, form a net zero charge. What really happens is sodium gives up an electron, and where does that go? It goes to the chlorine, and that's how you form it. If you ever have some time and want to have some fun, don't forget Dr. White's a chemist, go to YouTube and look up the reaction of chlorine with sodium. It's quite dramatic. It gives off a lot of energy. You see a real good flame from it. Don't try that at home. All right, let's try another one. Now, if we look at this one, I'm going to do this one, then I'm going to let you have some fun. What molecules form from magnesium +2 and bromine -1? Well, this is a +2. This is a -1. It has to add up to 0. Uh-oh, it doesn't. Well, you can't change the charge. You can't. But you can change how many there are. And how do I get to 0? Well, if this is a +2, I need -2. I know how I can do that. I'll do that. So how does this indicate what the formula of magnesium bromide is? It's 1 magnesium. And this tells me there's 2 bromine. And that's how I do it. I'll say it again. All molecules, I better write it. All molecules have a net zero charge. So the driving force is the charges from each ion have to add up in a molecule to 0. You can't change the number, what the charge is, but you can change how many they are. And what this tells us is there's 1 magnesium and 2 bromine in magnesium bromide. Your turn. Hold on. That looks like an E. That should be an F. What's the molecular formula of the molecule formed from sodium plus ions and fluoride minus ions? All right, let's take a look at this. Remember, someone wrote it right up here. That was nice of them. all molecules have a net zero charge. All molecules have a net zero charge. Therefore, this is a +1. This is a -1, the fluoride. Does this add up to 0? And the answer is yes. So the molecule would have this formula, NaF. Now, NaF is called sodium fluoride. And many years ago, I think it was about 1930, 35, researchers found there was this one town, I believe it was in Texas, small town, nobody had cavities. They all had great teeth. Dr. White inherited, well, I don't want to talk about that from heredity. But anyways, I don't want to talk. But they found this out and they searched what was the reason. And they found out that their water supply had a very high level of sodium fluoride, NaF. Now you know how that has that formula. And they said, well, if that promotes good dental hygiene and keeps your mouth and teeth nice and healthy, we're going to put it, one, in all the water supplies, and they are, and still to this day do, they put fluoride, sodium fluoride, and sometimes potassium fluoride, but usually sodium fluoride, it's cheaper, I believe, in the water system. Now, over the decades, a number of, how should I say this, groups that have unusual thought processes claim, oh, they're putting it in our water to control our mind and everything. No, well, it hasn't worked with me. Now, the other place, not to scare you, but the next time you're in your bathroom, where I assume that's where you keep your toothpaste, that's where Dr. White keeps his, look at the tube, and you'll see near the end on there, sodium fluoride. And if you look on the box, you know, with fluoride, that's why they put it in there, because they found out years ago in that town in Texas, it promotes good dental health. I just saw, Camille, thank you for your question. All questions are good. And the answer is yes. All numbers in a formula are always to the right subscript, always. That's a good question. But then again, you know, Dr. White knows all questions are good questions. And thank you all. You're getting the hang of it too. Oh, let's go and try another one. I already did this. Try this one. What's the molecular formula formed from the molecule that's got calcium +2, chloride -1? Go. In other words, start solving it. Everybody done? I think so. All right, let's take a look at this. What molecules form when you have calcium +2, chloride -1? And here, if we look at this, we have, this is a +2, and this is a -1. And it has to add up to 0. It doesn't. How do we change that? You can't change the charge, but you can change how many. And if I put a 2 there, you'll see that. And now it adds up to 2, and that means calcium chloride. I don't know why my pen's, that's why. All right, calcium chloride is CaCl2, 1 calcium cation and 2 chloride anions. Now, again, if you're wondering, why am I learning this stuff? Well, in about, end of November, right around Thanksgiving, maybe a week before, Dr. White will go to one of the big home improvement stores like Lowe's, Menards, or Home Depot. God, I gotta find a way when I say their names, they give me money, product placement, but next week. But I will buy calcium chloride. What is that? Have you ever seen the little white pellets or spheres that you buy in the big bags, 25-pound bags? And when you have ice on your driveway, like mine, you throw it out there. Let me bring my hand up. You throw it out, cover it, and come back in a couple hours, and it's all melted. Even though the temperature may be 10 above, it still melts it. And how does that do that? Well, I'll teach you later on in the semester. I'll give you a quick understanding now. When you mix two things together, certain things, you have what's known as, it's called the colligative effect. And that causes the melting point to lower. And that's what happens when you mix like salt, regular rock salt. If the temperature is close enough to 32, like I'm guessing now it's about 20, that will work. When it gets real low, like we had about 2 years ago when it was super cold, rock salt won't do it. You need the little white pellets, and now you know it's calcium chloride. And if you happen to be at a football party this weekend, or virtual football party, and you want to impress people and say, the little white pellets that you use on your driveway, that's calcium chloride, because it's a +2 cation and a -1 anion. People don't want to hear chemistry at parties. Don't. Well, we went through writing. I'm not going to do naming. Now, let's look at polyatomic ions again. Polyatomic ions are atoms that have acquired an electrical charge by sharing among atoms the electrons. And I've talked about some key ones like nitrate or nitrite, nitrate, sulfate, and these are key ions. And the question is, when you have this with other cations, and there are also cations which we could have this is the ammonium cation, NH4 plus, and there are others. Hydroxide is a minus, but these are key ones. What molecular formulas are formed when you use those ions? Well, let's take a look at this. What if we said, what's the formula of the molecule formed from magnesium +2 nitride -1. Well, all molecules have a net zero charge. This is a +2. This is a -1. Does that equal to 0? And the answer is no. I like to put, you don't have to, a line through there so you know that's not oxygen. Well, how do I do that? Well, just like before, you change how many. Now, here's the part I need to teach you. I have one magnesium, but now, how do I show there are two of these? Well, this is when you use a bracket. Bracket, put inside the polyatomic ion, close the bracket, then subscript, you put right here how many you have. In this case, 2. And now magnesium nitrite would be this molecule right here. And why don't you try this one? Have you found out chemistry isn't that bad? Might even be a little fun. And when you're done, give me a thumbs up or smile, or do both. Well, you can frown too if you want, but that's not as fun as smiling. All right, I think everybody's done. Let's do this. Remember, all molecules have a net zero charge. This is a +2. This is a -1. It has to add up to 0. Oh, it doesn't. You can't change the charge, but you can change how many. And I'll have 2 of those. How do I write calcium nitrate? 1 calcium. Then since I'm going to need 2 of these polyatomic ions, I'll put it in a bracket. And then how many do I need? 2. So subscript to the right of the closing bracket, I'll put 2. Oh, this is fun. Let's try another one. Sulfate is a, I have to think about my alphabet for a second. Hopefully I got it right. Dr. White was never good at the alphabet or spelling in first, second, third, fourth, fifth, sixth, whatever grade. Anyways, let's do this one. What is the molecular formula of the molecule with sodium cations +1 and sulfate -2? Have fun. I'm going to let you try this one, see if you can figure out how to do it. Then I'll show you. All right, anybody need more time? Going once, twice. All right, let's do this. Now, all molecules have a net zero charge. This is a +1. Oh, and this is -2. And why are you doing this? Hold on one second. And this has to add up to 0. It doesn't. What do I do? Well, if this is a -2, I need this to be a +2. I can't change the charge, but I can change how many. Now, if I have 2 of these, sodium, 1 sulfate, it will add up to 0. How do I show that? Like this. And this tells me there are 2 sodium and 1 sulfate. And that's how you do it. Now, sodium sulfate, which is this molecule, a lot of you have probably seen. Sodium sulfate. How many of you have ever purchased electronics or optical, like binoculars or other things? And even nowadays, you see it in food, like the roasted seaweed called nori. You see a little packet and it says, do not eat, absorbent. What's in there? That's sodium sulfate, Na2SO4. And it has the ability to absorb water. And that's why they put it in there, to keep moisture out of there so it doesn't damage whatever you're buying. So next time you see one of those, that's chemistry. Now, interesting story. Years ago, we had a flood in our house when I was in grade school, and we had a crawl space, and it had rocks in there underneath near the part of the foundation. And it got flooded too, enough water in there. And even though we had some dehumidifiers, my father, being a pharmacist who knew chemistry, why did I become a chemist? I don't know. But anyways, he hung bags. He was able to buy sodium sulfate, got some cheesecloth or muslin bags, and hung them from the wood joists in the crawl space, put buckets underneath. It absorbed the moisture from the ground that was in the air, dripped in the bucket, and we got that dry super quick. Unfortunately, it was my job to go in there on my hands and knees and empty the buckets, pull them out. But for my father, it was something I would do. Oh no, I looked at the clock and time flies when you're having fun with Dr. White in chemistry. Yep, I'll end a whole 30 seconds early. I'll see you in about 5 minutes. I'm going to do my stretching so I don't get any leg cramps by sitting for 2 hours straight. And I'm getting all choked up over it. And I'll see you in 5 minutes at 10:55. Come back.
Dr. White, could I ask you a quick question on that problem we just did?
Yep.
The way you showed the sodium sulfate was Na.
Hold on.
Oh, okay.
You see it now?
Yes.
Na2SO4.
Right. Would it be wrong if I left the plus sign with the sodium and the -2 on the sulfate?
Nah, technically yes, but I'd laugh and say, "Oh, look what you put in," but you don't have to.
Oh, okay. Because that's the way my answer came out.
Well, if you did, I wouldn't take points off, because essentially I know you knew what you're doing. But when we write molecules, formulas like you see there, except in some organic molecules, you don't show charges.
Oh, okay. All right. Thank
But
you.
if you do, don't tell anybody I'm being nice.
All right. Thank you.
You're welcome. Well, I better get you all back to class now. It's time to start again. And I was showing you with polyatomic ions how to draw the formula. Oh, let's do one more. These are fun. Let me think of one to do. And why don't you try this? Calcium +2, and this is called hydroxide ion. And when you're done, give me a thumbs up. All right, I think everybody's done. Let's do this. Isn't this real hard? Not really, once you know how to do it. Remember, all molecules have a net zero charge. And therefore, if I look over here, I have a +2 and a -1. Does that add up to 0? No. So, and let me do one thing here. So how do we do that? We can't change the charges, but you can change how many. And if I have 2, this would be a +2. 2 times -1 is a -2. That now adds up to 0. So what does that tell me? I have 1 calcium. And now since I have a polyatomic ion, I need more than 1. I'll put it in a bracket. How many do I need? 2. So I do that. And that's the chemical formula for calcium hydroxide. So all ionic compounds are governed like that. And you have cations and anions coming together, forming ionic bonds. And always the net charge is 0. All right, let me go through that one again, because I see a couple people have questions, and all questions are good questions. Let me keep the chat box open. All right, here we have calcium +2. This whole thing, O and H, hydroxide, is together like a unit. And we'll talk more about how it's stuck together when we go over covalent bonds in a little while. But this has a negative charge for this whole thing. It's like a unit, like your hands all together, fingers, palm, and etc. And now, and I didn't have to put the negative charge there. Sometimes I'll do that without thinking. And now, since this is a +2 and this is a -1, we need 2 of these, and that's why I put it in a bracket there. And technically, both of these still have the charges that you see up here, but when we write the formula here, you don't usually show the charges unless you do what Dr. White did. Now, if on a test you were to put a charges here, like a +2 and a -1, I'd smile at that, but I wouldn't mark it wrong. And now you have everybody around you as witness. I said that. Plus, it's on the videotape. Why? I just got convicted. No. All right. And that's how you form ionic compounds. Now, let's talk about the other type of chemical bond, and that's the covalent bond. And in your book, they say between similar and ionic atoms. That's okay, but you don't have to know that. It's called a molecule. This I'm not going to get into. I call all ionic and covalent molecule, but this you should know. It involves sharing pairs of electrons. A covalent bond is sharing one or more pairs of electrons between 2 atoms. Wow, deja vu. I bet you this, I'll say it again. A chemical bond, what's a covalent bond? A chemical bond between 2 atoms from the sharing of electrons, or just think of it easiest way, sharing a 1 or more pair of electrons between 2 atoms. Here's from your book, 2 nuclei, and you can think of that as the nucleus. All right, let's look at the simplest covalent molecule, hydrogen gas. And here we have hydrogen atom has 1 electron. You go in the periodic table, you see its atomic number is 1. Well, exists as the gas as H2. By the way, Dr. White's worked a lot with hydrogen gas. And how many of you have ever heard of hydrogenated fats and oils, like in your food that are unhealthy? You take fats and oil and react them with hydrogen, and that's how you make it. You take my organic chemistry, I'll explain why they do it and show you how that does it. I've worked with multi-tons at a time hydrogen gas in my career. Well, let's look at the structure. It's H2, and let's look at the Lewis structure. How many valence electrons does hydrogen have? And if we go to the periodic table, you'll see here's hydrogen. Look on top, 1 valence electron. Now, this hydrogen has 1 valence electron. This one has 1 valence electron. And this one says to the other, hey, look, I have an electron, you have an electron. Let's share. So we have a pair. And they do. And you draw it this way. And the only electrons that are ever shared are the valence electrons, the outermost electrons, which is why I really like valence electrons. All the chemistry I've ever done deals with valence electrons. And hydrogen has a stable outer shell now. And I'll explain more in the next one. So this is hydrogen, and here's the Lewis structure. Now, the Lewis structure shows bonded electrons. Those are pairs of valence electrons that are shared in a covalent bond. By the way, the 2 electrons here between the hydrogen, that's a chemical bond, a covalent chemical bond. You're sharing 1 pair of electrons between 2 atoms. Now, sometimes you'll have electrons, valence electrons around an element that are not involved in a, by the way, switches on since I started talking about covalent bonds, in case you were wondering. But sometimes you'll have valence electrons that are not involved in a chemical bond. We have a name for those, the non-bonding electrons. Those are always pairs of valence electrons that are not involved in sharing. Now, I'll never ask you what's a non-bonding electron, but I might ask you to circle them in a Lewis structure. Now, one of the things that, I don't have a slide, what's the driving force? And that is the octet rule. And that is, as I have earlier slide, atoms gain, lose, or share, and covalent bonds is sharing to get 8 valence electrons. And that's why it's called the octet rule. Now there's one exception to the octet rule, which the atom or element doesn't get 8 valence electrons, and that's hydrogen gas, as you saw up here. Its octet is really 2. Now, if I were to look at this pair of electrons and say, well, this hydrogen has those pair, it's got 2. And I could look at the other hydrogen and say this one has 2, the 2 it's sharing, so they both have their octet, but for hydrogen, the octet is 2. All right, let's see what this means. Again, the driving force is atoms of elements for covalent bonds shares pairs of electrons to get 8 valence electrons. So let's look at these, practice the Lewis structure for key molecules. Let's take a look at chlorine. Now, first thing you have to do, if I were to ask, draw the Lewis structure. If I were to ask for chlorine, what do you have to do? First, you have to find out how many valence electrons chlorine has, because whenever you see the name Lewis, we're talking about valence electrons. How do you do that? You go to the periodic table. If I go here, I look, oh, there's chlorine, Cl. look at the top and see the number 7, Roman numeral or numeric, and I know chlorine has 7 valence electrons. So now I know chlorine, 7 valence electrons. And you don't have to do it this way, but I'm showing you how it happens. This is 1 chlorine. And this is the other. And this one says, oh, I've got 1 electron. You've got 1 electron. Let's share. And they do. Now, the electrons all around that are not, that are pairs, those are non-bonding electrons. And this is how you draw the Lewis structure for chlorine gas. I've worked with chlorine gas. It's really nasty stuff, dangerous stuff, but it was something useful for what I was trying to make, and so that's why I used it. First of all, if we look at this, these are your bonded electrons. And now, if we look, and I'm not going to circle all of them, the ones that are not involved in a chemical bond, covalent bond sharing, these are your non-bonding. Ran out of room there. Are non-bonding, and they're more here, they're more here. Any pair that's not involved in the bond. Now, let's see if I have any more colors that don't look too obnoxious. Let's see, is this green? That's not too bad. If we look at this chlorine, it has these non-bonding electrons, and this bonded. So if I go like this and count all the electrons around this chlorine right there, 2, 4, 6, 8, octet. And I can do the same for here, octet, and both chlorines have an octet, and that's how you do it. Now, why don't you try for HCl? And the first thing you have to do, hydrochloric acid, HCl, is find out how many valence electrons does hydrogen and chlorine have. So there's a periodic table to help you out. Again, you're drawing the Lewis structure for hydrogen chloride. Remember, if you finished early, let's give everybody time to do it. Remember, when you're done, give me a thumbs up. All right, I think everybody's done. Let's take a look at this. We're trying to find a chemical or draw the Lewis structure for hydrogen chloride, HCl. Hydrogen has one valence electron. Look at the top. Chlorine, don't look at the electrons here. That's total. We're only looking at the valence, the outermost. It has 7. So let's go back to our whiteboard. I can do it on here. Hydrogen, oh, I don't like that color. Hydrogen has 1 valence electron. Chlorine has 7 valence electrons. Now, this part you don't have to do, but I will to show you how it's done. Remember, you put 1 on each side and then you start doubling up. Hydrogen says, oh, look, I have 1 unpaired electron. You have 1 unpaired electron. Let's share. And they do. And how do they share? Like this. Don't forget to put the non-bonding electron pairs, which is what I'm doing now. And if we go look at this molecule, counting the bonded and the non-bonding electrons on chlorine, how many dots or pairs of electrons do you see there? 8. It has an octet. Now, if we look for a hydrogen, they're just 2. But remember, hydrogen's octet is 2. So everybody's happy because they're nice and stable. They have their octet. Oh, let's do one more. This is going to be a little tough, but I think you're up to it. Why don't you draw the structure, Lewis structure for water, H2O? Now, let me give you a hint. For this one, the oxygen is in the center. That's the only way it will work. And here's your periodic table. One of these days, I'm going to have to tape the game show music from TV and play it. Nah. You like The Price is Right? Is that still on TV? I haven't watched that in decades. Or Jeopardy. I haven't watched that in decades either. I was never a big game show TV person. Still I'm not. Remember, each atom wants to get its octet. I give you another 35 seconds, and then we'll start going forward on this. Unless all of you are done, give me a thumbs up, and I'll start now. All right, looks like everybody's giving me a thumbs up. Those of you who like to give thumbs up. So let's get going on that. All right. Hydrogen, 1 valence electron, and you look at the top of the periodic table. Oxygen, 6 valence electrons. Again, look at the top. Now, this hydrogen has 1 valence electron. This oxygen has 6, 1 here, plus 2 pair. Another hydrogen has this. So the Lewis structure for water is this. Looks cleaner. And if I take my pen and circle the bonded and non-bonding electrons on each atom, let's look at oxygen, 2, 4, 6, 8. So if we look here, it's got its octet. Now hydrogen has 1, 2 it's sharing, and that's got an octet. Remember, hydrogen's octet is 2. That's the one exception to the octet rule. And this one, same thing. And the next time you're at a party and you see someone drinking some water or something with water in there, remember, what's the covalent bond? A sharing of pairs of electrons. You can tell them, do you know there are 2 covalent bonds in the water you're drinking? Don't. People do not want to hear that when they're drinking water. Let's do one more, and I'm going to do this one. And this is ammonia. And ammonia is NH3. Ammonia is a very important compound, and I'll teach you later that a very important reaction that was covered by 2 Germans, Haber and Bosch, back about 1908, 1910, changed our world. Yes, this little molecule changed our whole planet. Molecules can do that. But let's look at the Lewis structure. Ooh, I'm going to make you do a little work. Why don't you take a 8.9 second, I'll give you 15 seconds. What are how many valence electrons hydrogen and nitrogen have? Time's up. Hydrogen, H. Look at the top, 1 valence electron. Nitrogen, N. Look at the top, 5 valence electrons. Now, what I'm doing here, you never have to do that on test, but I'm showing you everything that's going on. And I have nitrogen will be in the middle. That's the only way you can do it. It's got 5 valence electrons. Remember, you put 1 on each side. Now, chemists like to put the lone pair non-bonding electrons on top. Now, each hydrogen has 1, so it says, oh, look, you've got 1, I've got 1, let's share. Same thing here. And same thing here. And now, if we look at each atom, the question is, does it have an octet? Well, if we look at the nitrogen, 2, 4, 6, 8. Who do you appreciate, Dr. What? No, anyways. Oh, high school cheer came out. But anyways, nitrogen has this octet. Now, if we look at each hydrogen, I'll just do one, it has a pair of electrons shared between the nitrogen and the hydrogen, and we count that when we're counting. And here we have 2, and remember, hydrogens, the only exception of all the elements, its octet is 2. And here in ammonia, we have, look out, I'm going to go full Technicolor on you. 1, 2, 3 pairs of electrons. So there's 3 covalent bonds or chemical bonds, but covalent bonds in ammonia. Now, I don't know if I mentioned this before or not, but do you know who's the greatest of all chemists? Mother Nature. And Mother Nature is pretty cool what she did in chemistry and still does, especially organic chemistry, but regular chemistry, she's pretty cool too. And I have no idea why that's better. All right. Single bonds are very important. One pair of electrons are very important, as you just saw in ammonia, water, and chlorine gas and hydrogen gas. But Mother Nature, she's cool. And there actually is 3 types of covalent bonds. And there are 3 of them, 3 types of covalent bond. And hold on, I see a question. The answer is, Camille, yes. On top, those are non-sharing electrons. Doesn't that make you feel good? You know that? And if you think about it, on the block where you live, most people don't know that. So see how much knowledge you're getting from chemistry? And Dr. White. Thank you for asking. All right, so let's look at the 3 covalent chemical bonds. And by the way, I better tell you this and get to the right color. Oh, it disappeared on me. You should know this. The first type of covalent bond is a single bond. And you should know a single bond is a bond in which 2 atoms share 1 pair of electrons. Single bond sharing 1 pair of electrons between atoms. Next one you should know, double bond. And a double bond is a bond between 2 atoms in which 2 atoms share now 2 pairs of electrons. Single bond, 1 pair being shared, double bond, 2 pair, and the last one, but not the least, triple bond. And triple bond is a bond in which 2 atoms share 3 pair of electrons. So you have single, double, triple bond. And at this time, if we were in a classroom together, I would ask everybody, all right, everybody together, what are the names of the covalent chemical bonds? and we go back to the slides, and I ask you out loud, everybody loud, and you say single bond, double bond, triple bond. I don't know if your voice will get that low, but triple bond. And those are the 3 covalent bonds. First one, single bond, you should know that's sharing one pair of electrons. Next one, double bond. You're sharing 2 pairs of electrons. And the last one, a triple bond. And there you're sharing 3 pairs of electrons. Single bond, everybody together, single bond, so I can hear you in my office. Louder, single bond, double bond, triple bond. Now, let's look at this. And the question would be, draw the Lewis structure for compounds with multiple bonds. Let's do nitrogen. Let me take you to my whiteboard. This is nitrogen gas. You're inhaling right now, if you're breathing, and I hope you all are, nitrogen gas along with oxygen gas. So how would you draw the Lewis structure? Well, each nitrogen has how many valence electrons? I'll let you figure that out. I'll give you 3.2 seconds. 3.1, 3.15, time's up. Nitrogen, and look at top, 5 valence electrons. So each nitrogen has 5 valence electrons. Well, there are 2 of them. Now, what I'm doing here, you don't have to do on a test, but this will help you understand. So I'm going to put 1 on each side. That's 4. Now double up. 1 on each side. Now double up. Now, this nitrogen says to the other one, I have 3 unpaired electrons. You have 1, 2, 3 unpaired electrons. Let's share. The non-bonding electrons are still coming along for the ride. 1, 2 pair, 3 pair. And what do we call that? This is a triple bond. And here I have 3 pairs of bonded electrons, and each one of these are the non-bonding electrons. Now, atoms share electrons in covalent bonds to get an octet. If we look at this nitrogen, it has these 6 electrons plus this 2, 6 plus 2, 8. It's an octet. We look at this nitrogen, it's sharing these electrons plus 2, it's got an octet. So nitrogen gas that you're breathing right now has a triple bond. So think about it. When you're inhaling a molecule that has a triple bond, because air is approximately 80% nitrogen gas and 20% O2 oxygen gas. Ooh, I'm going to let you try that one on your own. And if you look at a periodic table, wait a second, I'll let you do. First of all, you have to figure out how many valence electrons. If you look here, oxygen on top has 6 valence electrons. And now it's your turn. When you're done, give me a thumbs up. If you're having trouble, don't forget, you're always welcome to come to my office hours Monday and Wednesday night. And sometimes the first time you're learning something can be challenging, so don't get discouraged, because I gave you practice problems when you do this chapter to do your own, more of them. All right, let's take a look at this. If we look at this, oxygen has 6 valence electrons. There are 2 of them, so I have this oxygen and this one. If I put in my 6, and this part you don't have to do on a test, but I'm showing you what's happening. I do the same for this one. And now we look at this and says, this oxygen says, oh, look, I have 1, 2 unpaired electrons, and you have 1, 2 unpaired electrons. Let's share. And they do. And it looks like this. The non-bonding electrons are still there. But now 1, 2 here, 1, 2 unpaired here, they're sharing. And this is the Lewis structure for O2, what you're breathing now, oxygen gas. And what kind of chemical bond exists between oxygen atoms in oxygen gas? I'm going to let you think about that for about 8.6 seconds. Remember, there's single, double, and triple bond. Time's up. 2 pair of electrons. That's a double bond. And if we look at each atom, this oxygen has these pairs of electrons plus the ones that are shared. 2, 4, 6, 8. Octet. Same thing on this side. 2, 4, 6, 8. Octet. So everybody's happy. And that's why oxygen is O2, not O7 or any other thing. And the next time you're at a party, do not tell someone, you know, when you're breathing like that, you're inhaling oxygen gas that has a double bond. Don't do that. Now, for those of you who know baseball, what happens when you go to first base? What do we call that? A single. 1, first base, single. When you go to second base, what do you call that? A double. And we go to third base in baseball, what do we call that? A triple. I wonder if whoever came up with the name single, double, and triple was watching baseball when they did that. In case you want to learn how to remember that, that's a good way. Think of baseball. All right, I'm going to do something because today's lab, I can get you out of here real quick. We can either take a 5-minute break and be done in 10 minutes, or we can just go right through and do 10 minutes. I think you can hang in there. I'll get you out early. All right. Hold on. It's lab time. And let's have fun with labs. But first I see a question. The answer is, on a test, would I ask you to write the Lewis structure specifically for single, double, and triple bond? Ooh, that's a good question, but no, that would be cruel and unusual punishment, too hard. By the way, at least right now, until maybe it's changed, I hope not, the Supreme Court has outlawed cruel and unusual punishment to students, so no, I wouldn't do that. What I would ask you to do is draw the Lewis structure of water, draw the Lewis structure of, say, bromine gas, draw the Lewis structure of oxygen or nitrogen. There are a few more I'm going to show you, but I want to get on to the lab today instead of keeping you, because afterward you want to take a test. Hopefully you'll all do real good, and you don't need luck, but I hope you all do well. One thing for today's test, take your time and read all the questions, each one clearly. Don't rush through it, because people sometimes do that and think it says one thing. I try and be clear when I write them, but because they're rushing, they make mistakes. Don't. And by the way, Kim, you're welcome. All right, lab time. Let's talk about lab. How many of you have ever gone to the supermarket, pick up something, you look at the label, oh, look how many calories that is. Let's take a look at one. I haven't done this, so let's see what happens. I shouldn't do this. But if you look at the back of the label, they've got it right here so you can see it. And can everybody see the internet where it says 160 cal? I don't want to see that. I'm going to hide it. But anyways, that's my favorite potato chips. But anyways, I don't keep it in the house because they disappear immediately once the bag is open, which is quite sad. They just go, boom, we're gone. But anyways, where did I get this number? 160 calories per serving size, 28 grams, 1 ounce. How did I get that? Well, it turns out calories is a measure of heat, how much, or energy, how much energy. And one way to determine energy of a food is by burning it and measuring how much heat is given off. And we do that in what's called a calorimeter. And a calorimeter is a device that has water in there, and you measure the change of temperature when you burn something of the water, because the water captures the heat that's given off by whatever burning. And how does it capture it? By having its temperature go up. And there's a formula, how much water, what's the change in temperature, and then there's a very important conversion factor called the specific heat. How much heat is involved for so much weight of water or any compound you can find it, but water is the best for so many degrees change in temperature. And that what would be the lab today. I have it as a peanut. Quick story, a number of years ago, I was teaching, we were doing this lab at Elgin Community College, which we also do a similar one as COD. And it had been on the news, and it's an important thing, but it was sort of new about peanut allergies and how severe people can suffer when they're exposed to peanuts who have that allergy. Well, the following week, I was going to teach this lab, and in the past, we'd burn peanuts, which would fill the lab with some of the residue of the peanuts. And I don't know what made me do it, other than concern for my students. And a week before, I said, yeah, I just saw this thing about peanut allergies. How many of you have peanut allergies? And 2 people raised their hands. So immediately I contact all the other faculty. What do? I'm not going to have them use peanuts. These people can get sick. So we thought about it, and I didn't come up with it, but another faculty said, let's use corn chips. And turns out Fritos, corn chips burn real good, so do peanuts. And let's look at the lab. This lab is in the assignment area of Blackboard. Oh no, I lost it. Hold on one sec. All right, you should all see the lab right now. Thumbs up, people. Can you see calories in a nut? Thank you. All right, what you're going to be doing if you were at home is determining calories in a nut. Like if you got Planters peanuts, or dangerous thing for me is the cashews that I get, and I don't buy it too often because they evaporate real quick, from Costco. I love cashews. Peanuts are good too, but I don't like walnuts. My father liked them, but I never did. And still don't. Now, when you burn it, the flame will be captured by the calorimeter. And you can find the starting temperature and the final temperature of water. This is called delta T. Delta in chemistry or in math too means difference. Delta T is the difference in temperature from what you start and what you finish. And you can calculate the heat given off in the nut, and therefore calculate the heat and therefore the calories in a nut. Now, this is called calorimetry, and calorimeters can be very expensive. Some of them at the National Institute of Bureau of Standards have calorimeters that cost tens of thousands of dollars. If we're doing it in class or the lab, really, you'd be using an empty pop can, which I think you can figure out isn't tens and thousands of dollars. So it's not as accurate, but it still gives very good results. The first time I taught this lab, I was amazed how good the results the whole class had doing this. And we had fun burning peanuts and then later on corn chips. I mean, the flame gets really high. This stuff is quite flammable. And the difference is delta T along with the heat capacity of water. This is a constant that's calculated that you can find in the literature on the internet. And that tells you how much energy to heat a gram of water. And from that, you can calculate the calories in a nut. Now, let's see how long this video is. I'm going to tell you what. Well, let's watch a little.
I'm going to be conducting the calorimetry lab with
Let's
a
all
peanut.
watch this.
The first thing you need to do is read through your lab and then make sure that your setup looks like mine does here. Make sure also that your stick for the food source is measured out as being only 3 centimeters away from the base of your can. So make sure to measure that. You're going to need 100 milliliters of water that you will pour into your can.
We
The
use
water
200.
temperature is what you will be recording initially and then after the food source has burned. Go ahead and place a thermometer into the can and let the thermometer adjust to the temperature. While it adjusts, I'm going to take the mass of my food source, which is a peanut. The mass of my peanut is 0.5 grams. You need to record that into your data table. The temperature of the water in my can is 24 degrees Celsius. Very carefully place your food source onto the pin.
We use a paper clip that's
And then you need
folded.
to start your food source on fire. I'm going to use a candle to do this because it does take some time to start the food source burning.
We use a butane lighter.
Be very careful with matches.
Check out the flame on this, how much.
Once the food source has caught on fire,
White, we're not able to see the video.
I will go ahead and place it under the can.
Can you
with
see,
the water in
everybody
it
see this?
So that the temperature can be
No?
We can't see the video.
All right, hold on, we'll start again.
You'll start to hear some little,
Some. Can you see the picture on the screen right now?
Yes.
Yes.
All right, let's, instant replay. It's a short one.
conducting the calorimetry
Can you see
lab
everything
with a
now and
peanut.
hear it?
The first thing you need to do is read through your lab and then make sure that your setup looks like mine does here. Make sure also that your stick for the food source is measured out as being only 3 centimeters away from the base of your can. So make sure to measure that. You're going to need 100 milliliters of water that you will pour into your can. The water temperature is what you will be recording initially and then after the food source has burned. Go ahead and place a thermometer into the can and let the thermometer adjust to the temperature. While it adjusts, I'm going to take the mass of my food source, which is a peanut. The mass of my peanut is 0.5 grams. You need to record that into your data table. The temperature of the water in my can is 24 degrees Celsius. Very carefully place your food source onto the pin. And then you need to start your food source on fire. I'm going to use a candle to do this because it does take some time to start the food source burning. Be very careful with matches. Once the food source has caught on fire and is burning, I will go ahead and place it under the can with the water in it so that the temperature change can be recorded. You'll start to hear some little kind of clicking when it starts to burn. That is a little indication to you, like kind of popping, that the food source is on fire on its own. You're going to let that burn and heat up the water. Now that the peanut is completely burnt, you're going to check your ending temperature on your thermometer. For the data for the peanut, you're going to record a temperature of 33.5 degrees Celsius. You will be conducting this lab with 3 other food sources. The
All right, you're just going to use one food source. And the important, first of all, since Zoom is being funky with me today, everybody see the lab now on their screen? Thumbs up, people. Can you see it? Thank you. All right. The important formula, Formula A, is mass of water in kilograms times temperature difference delta T times the specific heat of water in calories per kilogram degrees C tells you how many calories in your nut. Now, the specific heat of water is 1.00 calories per kilogram degrees C. And the weight of your nut, by the way, if you were in our lab at COD, you'd use much more accurate balances that are 4 significant figures past the decimal. She just had 0.5, you'd get 0.5 something, something, something. And you'd measure the initial weight of the nut and the final one after you burned it. She didn't do that in the video. Also, side note, in the video, you could tell the student who did that didn't understand flames. The hottest part of a flame is at the top or a little above that, where she was holding the middle of the flame near the nut, which is why she had so much trouble catching it on fire. Now, you'll get the calories of your nut, and you'll divide that by the weight of the nut consumed, which will give you, like you see on the package, of Frito-Lay, not Frito-Lay, Lay's potato chips. Now I'm getting myself hungry, bad Dr. White, maybe you too. You'll see calories per gram, that's how you calculate it. Now here's the procedure. Now let's look at the data and calculations. This is this way, if you were in the lab, I'd be handing you this to help you out with what's in your lab book. Now, the mass of the water has to be in kilograms. She used 100 milliliters, which is 100 grams. We always use 200 grams, which is 0.200 kilograms, 3 significant figures. Here's your initial temperature. Here's your final temperature. You've got to figure out delta T. That's 1 minus 2. I think you could do that. Next, you would have measured the initial weight. And the way we do it, we have a holder. So you get that weight. Then afterward, you'd have the weight of the holder and the residual. And the difference is the weight consumed, 5. Now, how do you calculate the calories in your nut? Dr. White tried to make it easy for you. Don't tell anybody I'm being nice. Use Formula A for number 6, which is this right here. Use the values and put it in Formula A. The ones in red. Here's your delta T. Here's your mass of the water. And here's your specific heat of water. Mass of water, lower, 0.200. Delta T, you've got to figure it out. This number is 1.00. You multiply that and you get this number. Is that the calories per gram? No. You have to take number 6 right here and divide it by number 5. And that's today's lab calculations. Again, if you have any problems, always feel free to come to my office hours or stay after class. Now, to make it interesting, I've got some questions for you to answer. And this is 1, 2, and 3. And with that, that's the lab. And I'll get you out a whole 20 minutes early so you can go take your test. Thank you, Dr. White. I need to hear that. But anyways, good luck. Don't forget the tests are due tomorrow. Don't forget today, or if you have to tomorrow, The lab we did last week is due, upload it. And that was the density lab. And today's lab is due next Thursday by the end of the day. And with that, I'm going to wish you a very special Happy New Year's, Lashana Tov, for those of you who are celebrating Friday night, sundown. For those of you who don't, have a great rest of the week. Gang gesund, be healthy. I'll see you on Tuesday. Bye.